some time to talk to Paul Picciuto, Evan Chen, and Samantha Smithies about chemistry and nanoparticles. What exactly are these nanoparticles?
Nanoparticles are microscopic particles. They're so small that their physical properties aren't constant, so they're size dependent and they vary based on what the particles are made out of.
Interesting. So with something that small, what can they be used for?
Well, Lindsay, we're interested in using them for MRIs as contrasting agents. The nanoparticles can be used to view images of soft tissues within the body.
How do these nanoparticles work to view such images?
They're injected into the body and they help the relaxation process to make a sharper and more intense image during the MRI.
What do you mean by the reaction time?
The body has hydrogen atoms that line up. Then, a frequency from the MRI machine causes a pulse in which the protons flip, then relax to a normal state. The reaction, which is the change in protons, is what gives the signal of an MRI.
Where does this work in the human body?
The water and different environments of the body give different relaxation times, so the computer generates an image from that scanning, and then the contrast agents alter the T1 relaxation against pure water.
What did you do to make your own nanoparticles?
To make nanoparticles, we added 0.625 milliliters of 2.0 moles iron 2 chloride to a jar. Then, after stirring, we added 12.55 milliliters of 1.0 moles of iron 3 chloride to a jar. After that, we slowly added 125 milliliters of 1.10 moles of ammonia with a pipette. We added about 50 milliliters per minute.
Once we were done stirring, we removed excess ammonia by drawing all the magnetic particles to the side of the jar and then removing the solid into a waste beaker. We did this 3 times, then after the particles were clean and most of the water was removed, we added 2.5 milliliters of solution to rinse and separate the last of it. After that, we moved around a magnet to test the magnetic properties of the iron oxide ferrofluid.
And what did you observe from your experimenting?
Well, Lindsay, we noticed that the substance was very dark, almost a deep brown. It had some solidity to it and was very attracted to the magnet.
We also used a vernier magnetic field sensor to observe the magnetic properties of the fluids.
Very interesting. Now to Evan Chen to explain the hypothesis for the experiment.
Well, thank you, Lindsay! The group used a 0-point ratio as a variation which altered the results of the lab experiment. The properties of the nanoparticles depend on their size and shape. Our hypothesis was that the lower the variation used would have a lower magnetic property compared to a higher variation such as 0.8. The magnetic properties from the 0-point ratio would be very weak in comparison to the 0.8 ratio. The nanoparticles with a weaker magnetic field would be less attracted to the magnet. We were correct with our assumption. The nanoparticles made with a 0.1 ratio variation had a weak magnetic field and a weak attraction towards the magnet. We observed the behavior of other variations such as 0.4 and 0.8 variations, and they had a much stronger magnetic field and a much stronger attraction towards the magnet, like we thought. And good night. Back to you, Lindsay.
Which compound, or compounds, do you think would be the best MRI contrasting agent?
In terms of chemistry, anything diamagnetic would be the least favorable option. Anything paramagnetic would be a better option. Specifically, in group number 15, the nitrogen group.
Why is this? What do diamagnetic and paramagnetic mean?
Diamagnetic means that an atom has all of their electrons paired and the spin is at 0, whereas paramagnetic means that there are unpaired electrons. In the p orbital, there are 6 electrons total with 3 different pairs. Because of Hund's rule, the nitrogen group has 3 electrons without pairs, making this column more paramagnetic than other groups on the periodic table.
Is there a future in the usage of nanoparticles?
There is definitely a future for nanoparticles. They're very important today with MRI research and with other imaging.
Interesting. Now to the biologists that worked with the chemists and their nanoparticles.
Here we have Casey and Pong, the biologists that test the results from the experiments done by the chemists. To test the toxicity of the final product, you used brine shrimp. Why did you use brine shrimp, and what did you use it for?
Brine shrimp can be collected in massive quantities for testing. We wanted to analyze the influence of nanoparticles, which we did by applying a dose of the nanoparticles to the shrimp. In running these tests, we can determine what level of the nanoparticles would be considered toxic for human life.
And how is this toxicity level determined?
The lethal concentration is determined by counting the shrimps that are affected or killed by the toxin.
How did you test this?
There was 5 solutions that we created for testing. Each concentration was reduced by diluting each tube. There was one tube to observe the behavior of the shrimp in their regular environment. Then the ratios of the nanoparticles to seawater went from 1 to 1 to 1 to 1,000 in the remaining 4 tubes.
Our first tube, we added 1 millimeter of nanoparticles and 1 milliliter of seawater in it. And for the second one, we added 1 millimeter of nanoparticles and mixed up with 9 millimeters of seawater. And for the first one, we obtained 1 millimeter solution from the third tube and then mixed up with the seawater, 9 millimeter seawater. And then for the last one, we obtained 1 millimeter solution from the fourth tube and mixed up with the 9 millimeter seawater. After we prepare all the nanoparticle solutions, we separate them into different molds by obtaining each of them of 2 millimeters, and then from there we observe the shrimp from the wells for 3 days.
And what did you find with the results? Did the shrimp survive?
Yeah, in each different dilution of the concentrate, the shrimp had less than 70% survival rate after 3 days. Lethal concentration is determined by how much solution will kill 50% or more of the population within 3 days. This is known as LC50. We determined that the nanoparticles were toxic.
And what kind of applications would this have for human life? What can you do with this information?
By using the brine shrimp as a model organism, we correlate that any concentration that harmful to them will be also harmful to human. And also the nanoparticles can be used in different types of testings in the body, such as MRI and other imaging.
Interesting. All right, great stuff, guys. I want to thank you for joining me. Thank you all as well for watching. Good night.